Junior Cycle Higher Level 2014 Pilot, Paper 1, Question 14. This is a functions question. You have two functions here. F is an exponential function and G is a quadratic. You're given a domain of 0 up to 5 and you're asked to graph these two functions on a coordinate grid together. You'd be expected to work out all the values from 0 up to for t from 0 up to 5, and there's space on the next page for you to do that. I'll go straight ahead and just plot the points. So we have, for the first one, the exponential function f. F is the function f of t is 2 to the power of t. So if we plot the points, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32. And we can draw a curve that goes through those points. And then if we look at the second function, which is g of t was 2, so t squared plus 2t plus 1. So when we work through those values, g of 0 is 1, g of 1 is 4, g of 2 is 9, g of 3 is 16, g of 4 is 25, g of 5 is 36. And again, we can join those points up. And then moving on to parts 2 to 5, they're asking you to show you're working on the diagram. So we'll actually just work our way through this. Part 2, use your graphs to find the difference in the number of bacteria predicted by Paul and the number predicted by Marie after 2.5 days. So 2.5 days is here, and we're looking at Paul, which is the exponential function, and Marie, which is the quadratic function. So we're looking at the intersections from 2.5 up. We're talking about that value and that value. So read off very rudimentarily. I can read off values as being 12 and 6. So part 2, we've got the difference between those two values. So I'm showing my workings numerically, and that would go obviously in the section on the next page, but we'll keep this one view. And then obviously you can see my workings here. I'm seeing the difference between those two values. The values are 6 and 12, so 6 minus 12 gives me my answer. The only thing to be conscious of to get the full marks is this is in thousands, so the actual number of bacteria that we've got is therefore going to be 6,000. Moving on to part 3, use your graphs to estimate the range of values for t for which both Paul and Marie predict there will be at least 20,000 bacteria in the colony. So 20,000 in the colony is, well, here's 20,000. So here we have Marie at 3.5. I'm reading off 3.5. She predicts there'll be at least or more than 20,000, but Paul only starts thinking there's going to be more than 20,000 a bit further on. If we extend it beyond, we can read off that value. We can say it's somewhere between 4.25 and 4.5. So I can say t will be 4.3 in days. I should point out to you that you might get a different value than your neighbour, but as long as you've been reading off your graph correctly and using a ruler, like I can't do this with the iPad, but using a ruler and drawing your lines accurately and reading off your values off of your graph accurately, then whatever you get, you'll get the correct marks for. So the answer for that question is actually t is greater than or equal to 4.3 days. The next part, by extending your graphs to estimate the value of t other than t equals 0, so they're talking about other than this point here where there's an intersection, where else is there going to be the number of bacteria predicted by Paul and the number of bacteria predicted by Marie being the same. So what they're asking us to do here is just to extend the graph beyond what we have already. So the curve is going to carry on up in that sort of direction, gentle quadratic curve, and then for the slightly more extreme exponential curve. So we get a intersection point of approximately 38,000 bacteria and a value of t a bit beyond 5. So it asks for you estimate the value of t. So my value of t, again, it'd be a case of just reading off a value. So I'm going to go with a value of 5.1. 5.1, 5.2 is roughly the same. Again, I've drawn this particularly well. You do a more accurate version than I would with your ruler and pencil. But t is 5.1 as being that's the moment when the two have roughly the same amount of bacteria. Moving on to part 5. We don't need to use the graph for part 5, and just so you can see, here are the workings that we were done for drawing the graph, and there's the workings for each of those previous 3 parts of the questions. So part 5, the actual bacteria is 1.6 times 10 to the power of 7. Which formula will be better? Well, to a certain extent, it's just a case of doing the calculations. So f of 14, what do we get for f of 14? So what's 2 to the power of 14 as an actual number? It comes up as 16,384. And doing the same for Marie's with the function g, I get 225. Now, just don't forget that these aren't actually sort of the actual values in terms of bacteria. We have to talk about this in thousands. So we get 16 million, which if we were to put in standard form, which would be 1.64 times 10 to the power of 7, and for 225 in thousands will give you 2.25 times 10 to the 5. So it doesn't take too long for you to realize that if the 1.6 times 10 to the 7 is the correct answer, then the formula that gives you the better answer after 14 days would be function f, and function f was Paul's, the exponential function. Okay, so in terms of reason, well, I suppose my workings show you the reason, and what we're going to say is Paul, the function f of t being 2 to the power of t, gives you the better answer.